is stored on a single file on disk. How a node of BTree is going to look like, getting the tokens. This is where my start table is going to happen. Can you see the flow that from VDBE we called a BTree function, from BTree function we are calling a pager function. If crash happened, we would have used this journal file. List of dirty pages in LRU order. Welcome to the free course of Databases in Depth by Educosys, where we are not only going to discuss the databases in theory, but we are also going to see the code in a lot of detail. And not just see the code, but debug the most common statements like insert, create, select, and so on. It is my guarantee that this is not only the most detailed, but also the simplest and the coolest tutorial series on databases on YouTube so far. The only thing is that 77-78% of you have still not subscribed. So even though it is completely free for you, hitting that just one button is going to motivate me so much. It is going to mean to me so much, you have no idea. So if you could just take a second to hit that subscribe button and share the series with anyone who is looking to become a better software engineer, who is interested in software engineering, it would mean the world to me. Now, without wasting any time, let's get started. Have you ever wondered which databases are used to store data on your mobile phone while using mobile apps? I think all of you will agree that some data is stored on mobile phone, right? Like for cases of offline usage, or simply you cannot make network calls for anything and everything, right? You do need to store some data on the front end itself. And same is the case for IoT devices. The basic thing is that you need some lightweight database. You obviously cannot use something like MongoDB or Postgres because you require a separate server running for those databases. So what do you use in such cases in mobile apps or IoT devices? The most common solution is SQLite, and that is what this video is going to be about. We are going to see the code in detail, but before we do that, let us understand what is SQLite and why is it so famous. SQLite is lightweight embedded serverless DB. What does this mean? Lightweight meaning it has literally few hundreds of KBs of footprint. Literally 200, 300 KB is enough. Obviously, the exact value depends on the OS that you're using, but that's it. 200, 300 KB should be enough. So it is very lightweight. It is embedded. What does embedded means? So whatever app you're using, the library, the SQLite library is embeddable in the same process. So you don't need like a separate process running for SQLite. So it is lightweight, it is embeddable, and it needs zero configuration. What do I mean by zero configuration? Literally no configuration, nothing. Just download the code, the open source code. Obviously, that is why we will be able to see the code. It is open source, so you can just download it. You can compile it using any C compiler and use it. There is no configuration required. Talking about some cool features, it supports ACID properties. So yes, it supports atomicity, consistency, isolation, durability. Also, if there are say power failures or system crashes, it has recovery of DB file. So we will actually look at the code at how is the data being stored on the DB file and how does this recovery happen. It is also thread safe, so it takes care of DB level thread concurrency. And also it is cross-platform. So it lets you literally move your DB file from one platform to another platform. Let's say you created your DB file in the Windows platform. You literally just have to copy, paste to a Mac platform, and it will work seamlessly. It will work identically. That is so cool, right? But out of all the features that I have talked so far, the coolest thing about SQLite is always going to be that it is one of the most simplest databases out there. Supporting so many features and still being so simple, the code is very interesting. How it is structured is going to be very, very interesting. But before we get into the details of SQLite architecture, it is very important for you to understand that databases like MySQL and Postgres are different from SQLite. Although all three of them support ACID transactions, you use SQL queries, these two are different. How? MySQL and Postgres are client-server databases. They are designed for large scale. They are designed to handle high performance, higher concurrency. So you must have seen them being commonly used in high-level system design in huge web apps like Netflix, YouTube, and so on, right? And you must have seen that we create different database server because they are designed like that. Versus what we discuss in SQLite, they are designed for small to medium applications like mobile apps, like IoT devices. They are embedded. They don't need separate process. So it is very important that you understand the difference between them. We will be discussing Postgres also in this course, but as we go ahead with SQLite, it is very important that you understand the use cases where it is a good fit. This is the SQLite open source code. This is what I will be cloning and showing you in detail. So here, as you can see, there's the source code inside this. There's ext folder where all the extensions are going to be there. There's test folder where all the test cases, scripts and all are written. So essentially our main goal is going to be to understand the source code, right? So this is what we have to understand. There's a lot of code, but the documentation of this is actually pretty awesome. I will add the links in the description, and also the official documentation page is also pretty good. So this is their official page, and if you go to the documentation, it is pretty detailed. So whatever I am explaining in this video, I have understood from this documentation. I have gone through it in detail. Even in the code, the documentation is pretty detailed. I'll be showing it to you that as we discuss each and every module and component, I will show you the documentation. I will show you the code as well. Let's get started. Let's finally get started with understanding the SQLite architecture. But to make things easier, let's get started with a quick overview, and then we will discuss this in a lot more detail and I'll show you the code. Now, to make things very simple, what we are going to do is we are going to divide this entire SQLite architecture into some components. To be precise, we will talk about 7 components and we will understand the code component by component, and then later we will stitch everything together while debugging. And to make things even more simpler, we are going to divide these components into 2 divisions. Let me explain by what I'm trying to say. So how do we talk to SQLite? How do we tell SQLite that, okay, do this, do that? We send some SQL commands, correct? Now these commands are in English. We say create table or select all from or insert into or update this or delete this. So the first thing that SQLite has to do is make sense of what we are trying to say, right? Because these commands are in English or they are in some form, right? In some particular format we are sending these commands. Now first thing that SQLite is supposed to do is make sense of these commands, and whatever instruction we are saying, generate bytecode instruction for that. So basically whatever we are trying to say, generate bytecode for that. So this is what our first division is going to be doing. What our second division is going to be doing is that it is going to receive this bytecode, and this is the division that is going to be responsible for actually doing the data processing. So we are dividing our components into 2 divisions. The first division is going to have 3 components. The second division is going to have 4 components. So the first division is only responsible for processing what we are trying to say and generating the bytecode. The second division is going to pick up this bytecode and actually do the data processing. Okay, let's talk about the first division of components first. So as we said, we are getting some SQL commands. Now how do these commands come? Like create table or insert into. So now this big command we are going to divide into chunks and understand that, okay, create is 1 token, table is 1 token, or insert is 1 token, and then into is another token. So what we are doing, whatever command is coming, we are tokenizing it and understanding, okay, these are the tokens that are coming. So the first component is going to be a simple tokenizer, that, okay, tokenize it. Now once we tokenize this, together we are going to understand, okay, does this statement even make sense? Is this a valid statement or not? What is it trying to say? Can we optimize it further? Like if I say into insert, does it make sense? No. Or if I say table create, does it make sense? No, it doesn't. Or if I say create into, does it make sense? No. So is it a valid statement? Do these tokens together make sense? Or what is it trying to say? Can we optimize it? All of this is going to be done by our parser. So first we have tokenizer, then we have parser. And then whatever parsing we have done, after that we can finally do our code generation, and this will be done by our code generator. Now this code generator will finally generate our bytecode, and this bytecode is going to be interpreted by our second division. Now these divisions, we can also call them as front end and back end, but don't get confused. This is not like a front end back end of the huge systems that we usually talk about. It is just division of the components, and because the first division, what it is doing, it is making sense of whatever we are sending. It is sort of like a front end of SQLite, and whatever are the other components, they're going to be doing the processing work, and that is why we can consider it like a back end of SQLite. But don't get confused by the terms of front end and back end, and that is why initially I use the terms divisions and not front end and back end. Now let's understand the second division or the back end of SQLite. As you must have understood by now, the first thing that this new division is supposed to do is to interpret or to implement whatever code instruction is given to us. right? So we are giving some code instruction in this bytecode. So the first component, what it is supposed to do, it is supposed to implement this. So this is the component that will actually be doing the data processing. This component is called Virtual Database Engine or VDBE, or you can also call it the VM, so which is virtual machine. So this component is essentially abstraction of a new machine altogether. This is the one that is actually doing the data processing. But what is happening over here is that this component is still viewing the data in terms of tables, rows and columns. That is how we view the data, correct? Now it is not like the data is stored in tables and columns and rows, right? Internally it is stored in some other format. But this component is still viewing the data in terms of tables and rows and columns, and the components that are below it, that is where the data is stored in some other form, and that is what we will understand now. Before I go to the next component, this is a reminder that we are going to be discussing each of these components in a lot of detail. We are going to be seeing the code, so it is going to become clearer. Just stay patient with me. It is very interesting, right? So what this virtual machine is doing is that it is just a component. It's not a different machine in the same SQLite code. It is just one small component, and what it is doing, it is actually doing the data processing. So when I show you the code, you will see that it is actually a huge switch statement. So what it is doing is that if my bytecode is saying that select something, it is going to actually do the selection. If it is saying insert, it is actually going to do the insertion. So that is where the data processing is happening. Now the components below that is where we will understand that how data is stored. So the next component that this VDB actually uses is B or B plus tree. Now there is a different video altogether where I have covered that why B plus trees are commonly used to store indexes and tables in databases. So you can refer to that video. The link is in the description. It is part of this entire free course. So what happens in SQLite is that there is a separate B plus tree for every table and every index. So there is one completely different tree for a table or for an index, correct? Now this VDBE or VM is going to use this BTree to insert or to delete or to whatever it has to do. It is going to use this BTree component. So VDBE is using this BTree component. BTree component is going to use the next component, which is going to use the next component. Now before understanding the next two components, it is very important to understand that how data is stored on disk. Because we are viewing the data in terms of BTree, that okay, one entire table. So we are visualizing it how that okay, this table corresponds to a BTree. Okay, so but then there is a lot of data inside this, right? Okay, there's data, there's data, there's data. How is it stored on disk after all? So that is what we should understand before going to the next components, and let me tell you that first. In SQLite, whatever data is there in a particular database, it is stored on a single file on disk. So there is a single file on disk corresponding to every database, and I will actually show this to you. As I create new database, there will be a new file that will be created. Suppose I create one more database, another file, another database, another file. So if I delete the file, the database is gone. So every database is represented by a single file on disk. Now what is a file actually? File is nothing but how does it look like? So if suppose this is a file, there's just some data written on it, right? So some data that is written on it. It is just some bytes put together, correct? Some bits. So there's like a lot of data. Now what we are going to do in SQLite is that we are going to take a fixed size. So by default, the size is 4 KB. We can also configure it, but for now, to keep the explanation simple, I'm going to say 4 KB is the default size. It is the size. So what we are going to do is we're going to take this one file, the disk file, and we're going to divide into that fixed size chunks. So if you're taking 4 KB, just divide the entire file into 4 KB ka chunks. So what it is going to look like? Okay, 4 KB, another 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 4 KB. And in SQLite, these chunks are called pages, which are represented by page numbers. So if we have to understand it in very simple terms, a single DB is represented by a single file on disk, and that is nothing but an array of pages, just some pages put together. So like page 1, page 2, page 3, page 4, page 5, like this. It is just an array of pages. And this is how your disk file looks like. Now next important thing that you need to understand is that this file is on disk, right? And the pages are within the file obviously. Now, how will a processing happen? Because the disk file is huge, when you want to do some change to a particular page, right? If you want to insert something or you want to get something or you want to write something, it will be done to a few pages, not to the entire disk file. The disk file is huge. And whenever you have to process something, whenever you have to make changes to the file, what you're going to do is you're going to take out a few pages of it, maybe like 1 page or 2 page. You're going to take out the page, put it into memory, like into RAM, or you can say into cache. So you're going to take those pages out that you need to be processed and put it to cache, correct? Because your DB file is on disk. Now if you want to process something, you have to take it out to memory, to RAM, correct? So you're going to take it out and use cache. So I will actually show you the code. And interestingly, if you have heard about caching even a bit, and if I ask you, do you know any one caching technique, you will probably come up with LRU, and that is what is used by SQLite. I will actually show you the code. See that SQLite is actually using LRU technique to maintain its cache, but we'll discuss it in a lot more detail. I will show it to you. But in order to understand the overview, what is happening is there is a disk file, there are pages. Now, whenever we want to process a few pages, those pages have to be taken out, put to cache, processed, and then something. Now, this processing is done by our next component, which is called pager. This pager component is actually extremely important and we're going to spend a lot of time on it. Cache management is just one of the things it has to do. So our asset transactions happen because of pager. The rollback thing that I was talking about happens because of pager. The locking mechanism is done by pager. So all of that is taken care by pager, and we'll discuss it in a lot of detail. I know there might be a bit of confusion right now that, we were talking about BTrees and suddenly we're talking about pager. How does that happen? Let me give you some idea, and then when we talk into a lot of detail, it will be clearer. See, BTree is what a concept. So tree is what? Okay, there are nodes, right? So BTree is also in the end a tree. Now, each node in the end is stored in pager. Now, note how is the page represented? By a page number. So our BTree component is going to say that, okay, get me this particular node. Essentially what it is telling pager is, get me this particular page and process it. So if we have to visualize it, the entire table. So when we say a table in SQLite, so the table is structured in a BTree. But how are those BTree nodes stored on the disk file? In the end, these are some pages. Now we have just one file. So we will see how a page looks like, how it together forms the DB file. But each page, they will be represented by a page number. Now one page can be a node corresponding to the BTree. So we will visualize it like this. We will see the code. Coming to the last component, it might be obvious to a few of you. In the end, what we have to do is we have to deal with a disk file. Now, what do we have to do when we talk about file? We perform a lot of operations on the disk file, right? We say open file or read file or close file. So I will actually show you that when I say create a new database, there is like an open statement that is called in the operating system, right? Because we are creating a file or we are opening a file, and then similarly we are closing a file. Just how we do like read, open, close, that is what is exactly happening. But since SQLite is cross-platform, we need one common interface which can say that, okay, oh, this is Windows platform. So, okay, we have to open like this. Okay, this is Mac platform. We have to close it like this, and so on and so forth. So that is what our last component does. We can call it virtual file system or VFS. You will actually see this variable being used a lot of times in the code, VFS, or you can also call it operating system interface. So it is like an interface that, okay, if this is your operating system, this is how you're going to open the file, or you're going to read the file or close the file, and so on. So these are the main 7 components that we have to understand, and we have to see the code. But you have understood the flow. So congratulations, you actually understand the overview of SQLite architecture. Now it will just become a lot more fun because we will pick up each and every component and we will see it in a lot of detail. We will see the code. And in the end, when I debug, suppose when I debug the create statement or insert statement, you will see that first Tokeniser is hit, then Parser is hit, then code generator is hit, then VM is hit, then BTree is hit, then pager is hit, then OS interface. So this is the exact order in which components or modules are called. So the basics are now clear. Let's get to the detailing. Before we move ahead, I would just like to take a minute over here to tell you that if you're preparing for interviews or if you're looking to become a better software engineer, I would love to be part of your learning journey and make it easier, faster, better, and more fun. I teach live. Plus, you also get access to the recordings so you can learn at your own pace, and you get a consistent teaching style because I teach all HLD, LLD, DSA, project-based courses where we cover industry-level projects like YouTube, WhatsApp, Zerodha. We cover MERN stack as well as DevOps, and we also have C++. Plus, if you sign up for any of our courses, you get lifetime access to all the batches, the past, present, future, everything. You also get access to our mock interview platform. You can come practice anytime. We are going to guide you. We obviously have doubt support as well. We are putting our heart and soul into teaching. So if interested, at least check out the site. All the detailed curriculums, the testimonials, the answers to all the general FAQ, everything is present over here. Just check it out. Educosys.com is the site. Plus, if you still have any questions, feel free to reach out to us at support@educosys.com. We will also guide you about what is better for you. At least check out the testimonials for now.
The best thing that I like about Educosys is their courses are live.
Keerti herself, the way she teaches, the way the courses are structured are actually the best part.
Their live classes and the very helpful Discord community.
I feel very confident as compared to what I was before these courses as a software engineer.
My experience at Educosys have been really great.
I feel more confident as a software engineer after enrolling in Educosys.
But for now, let's get back to the video. This is the cloned SQLite project, the same SQLite project that I showed you on GitHub. I have just cloned it and this is on my system, that's it. First, let me show you some important files so that you get used to the code structure and you understand it, how is the code written. So we are in the SRC folder and that is the folder we'll be focusing on. So let's see some important files. So here you can see there is auth.c, there is BTree files, right? So these are the files related to BTree. If you see, the documentation is just amazing. The detailing to which they have explained is just awesome. This is how I've understood the entire code. I literally went through all the files, read through the documentation. So if you see over here, like BTree int, so here they have literally shown that how a node of BTree is going to look like, what all things are going to be there inside it. So if you just go down, if you read about it, this is how a page is going to look like. So each BTree pages is divided into 3 sections. So you can see file header, page header, and see they have explained it in very awesome way. My goal is to make things simpler for you and to summarize things in as easy way as possible. And interestingly, if you see on the top of every single file, they have written this with the copyright statement. May you do good and not evil. May you find forgiveness for yourself and forgive others. May you share freely, never taking more than you can give. Okay, amazing, but okay, cool. So let's look at some very important files. So BTree files will be important for us. We will be going through them in detail. Other than that, what else will we go through in detail? So you can see there are some mutex files. So this is where our OS layer is handled. So the last layer that we just discussed, the last component. So this is the OS layer. Then you can see pager.c, pager.h, again very, very important files. So here you can see interface.SQLite page cache subsystem, right? And here you can see this is like the cache files. Then we will be covering in a lot of detail what exactly is SQLite 3 file. It is extremely important. It is the most important file of the project and I will tell you how it is generated, what it is in detail. Just give me some time for that. There is table file, then there are some test files. And after that you can see tokenized file is from where we will start. We will start understanding tokenization. Then you can see update.c, absurd.c. See, you remember VDBE component, the virtual machine component. So this is the header file for virtual database engine. So I told you, right, VDBE component. So that entire code is in these 2 files. Then other than that, VDBE trace, vtab. So these are the important files that we will be going through. This is utility file and so on. So let's get started with tokenized.c and let's understand the main functions that are hit while tokenization. In tokenized.c, the most important function that is going to be hit like so many times, we'll be just done with this function, it will be hit so many times, is SQLite 3 run parser. So what is happening over here is that we will get the entire SQL string that we will be passing. So like select all or insert into or create space table, and this is where the entire parsing is going to happen. So if we go inside this, so don't get overwhelmed by the lot of code. So if you see inside this, there is a very simple while statement. There's a while one statement. So does it go on forever? Of course not. We will see. So first of all, they are getting the tokens. So one by one in every loop, they will get the token like create space table. So first they will get the token create, then they will get the token space, then they will get the token table like this. And if you see, for every token type, there is like sort of a switch statement over here. Let me show you what exactly is happening. Now you can see there are different token types, right? Space, over, filter. We will see what it is. First, let's see what is happening in get token. So if we go over here, it is returning the length of the token that begins at that point. So here you can see again there is CC space, CC minus, CC LP. There's something happening over here. So let's see what is CC space. So it is nothing but a character class. So we are just figuring out whatever character that we are dealing with. Is it a digit? Is it a dollar? Is it a minus? Or is it a slash? Is it a comma? Is it and? So, or is it illegal, right? So we're just figuring out that whatever we are dealing with, what token is it, right? So this is where we are figuring out that what is the character that we have gotten. Accordingly, we are assigning a token type. So what is a token type? Now see, token type can be, for example, it can be table or it can be create. So you figure out that, okay, these characters together are forming this token. So create or table. So essentially when the parsing is going to happen, and I will show you this literally when we debug, that when we do create space table, we will see that the tokens that are identified will be say 17. Then there will be a token for space. So if I search tk underscore space, so you can see there is 184, okay. So there will be like 70, then 184, then create space, and then there will be table. So it will be 16. So we will see like this that parsing is happening and we can figure out that these are the tokens. Now corresponding to each token, there will be like a function called. So this is exactly where those things are happening, right? So this is where we are getting the tokens. So as you can see, this is literally a huge switch statement, right? Is it CC pipe? Is it comma? Is it and? So you're just assigning a token type to it, okay? And let's get back to our parser. So now that you have a fair idea, rough idea of exactly how tokenization is happening, we're just basically going through every character by character and then putting some valid characters together and saying that, okay, this is a keyword, this is a token. Now we have tokens, and now we should understand a bit about how exactly parsing is happening, right? So after tokenizer, there is parser. So let's look at a very, very important file, which is parse.y. Now you would be thinking that, Keerti, parse.c and h makes sense. What is .y file? Now let me explain to you. So if you know a bit about parser generator, this will be easier. If you don't, it's fine. Let me just tell you in very simple terms. So earlier there were some parser generators named YACC and Python. Now SQLite has written their own parser generator, which is called Lemon, which is more easier, it is simpler. So this file contains SQLite's SQL parser in very simple terms. Now what is happening inside this? What does this file look like? Now I will make it very, very simple. Just look at this one statement. So look at this statement. Suppose this is where we are saying the create table statement parser generator is there. What does it mean? See, what exactly happens in parsing? We say that, okay, these are the tokens. Now we should know that these tokens should come exactly in this order, right? Because table create and create table are different orders. So there are some rules corresponding to it. So if these tokens are coming in this order, if they're following these particular grammar rules, then we can call this function or we can take this action. This is exactly what is happening in parsing, right? That if I have tokens which are following this particular grammar rule, call so and so function or perform this particular action. That is exactly what is happening. See, here we are saying that this is the grammar rule in very simple terms, and we are saying that call this particular function. Okay, and what is happening inside this function? So if you see SQLite 3 start table, if I just search for this, this is what is happening over here. So if you see, this is where it is telling, see, this is where parsing will be happening, and this is where we will tell that, okay, these were the tokens that were sent And this is the function that we have to call. So if I go inside this, particular function, you can see this is where my start table is going to happen. So there is a parser generator which is going to say, see, if tokens are coming in this order, then you call this particular function, which is this start table function, and this is where our, we will begin constructing a new table. So if you see like this, there will be all the statements. So like this was for start table, right? This will be similarly. So if we want to see more statements, let's see. So you can see create view statement, the drop table statement, then select statement. So see, select query should look like this, and after that you will call SQLite 3 select. Like this, we can keep going through a lot of statements in detail, but for now, to summarize it in a very simple terms, we first saw tokenization. What is tokenization? You take the SQL query that is coming, you divide into tokens, and then parsing what is happening. So yeah, we have a parse generator which makes sense of these tokens put together, that okay, this is the action that has to be performed. Like for example, we saw that start table is one action that has to be performed. So if we come to start table over here, and if we go down, see, there are a bunch of things that are happening over here, and I will explain this to you. We will debug this also, so just stay with me. So first thing, we are reading schema. This is one crucial thing. I will explain you why it is crucial. And other than this, if you go down, you will see there are a lot of VDBE calls that are happening, right? So what was the order in which the components were called? There was tokenizer, then there was parser. Then before VDBE, there should be one more thing, right? Which is what? Which is code generator. So we have to make sure that whatever we are sending to VDBE actually makes sense. It is bytecode. So first, let me tell you exactly where that happens, and then we can see that how the call to that bytecode generator is happening. Let us go through that first. So for that, one very important file is prepare.c. If we come over here, so see, if we go to the file, this file contains the implementation of SQLite 3 prepare interface and routines that contribute to loading the DB schema from disk. Okay, and the most important structure is SQLite 3 prepare. And if we go to this statement, so let me actually just go to this. So here, okay, let's go to this. This is very, very important. An instance of this object represents a single SQL statement. So whatever statement is there, like create table, insert into, select all, that has been compiled into binary form. So this is the binary code that we are generating and we are sending to the VDBE or VM. So this is the SQL statement compiled into binary form, and it is ready to be evaluated. Think of each SQL statement as a separate computer program. The original SQL text is the source code. So this is exactly what our first division of components were doing, right? The front end. What was it doing? It is just making sense of whatever SQL statement has come to us. And what is the final output? The output is this SQL 3 statement. A prepared statement object is the compiled object code. All SQL must be converted into prepared statement before it can be run. Who is going to start running it? The first component is going to be VDBE or VM. The life cycle of a prepared statement object usually goes like this. Create the prepared statement object using this prepare v2. So this seems like a very important function, right? So we'll see SQLite 3 prepare v2. Bind values to the parameters. So this will just say, okay, this is the meaning of this statement. Then we have to bind the values. Like for example, if table name is there, then we have to say, okay, this is the table name. And then we are going to run. So the running of the SQL is happening where? In SQLite 3 step. So these are the very important functions, SQLite 3 prepare to SQLite 3 step. And once it happens, after that SQLite 3 reset is called, but destroying the object is happening in SQLite 3 finalize. So any statement that is being called has to go through these three very, very important functions that we should understand: prepare v2, step, and finalize. So every time a particular statement is called, we have to see that these three functions are called or not, and it should be in this order. First we have to prepare the statement, then we have to execute the statement. This is where the running is happening, and this is where we are destroying the object. That okay, it has been run now you can destroy. Now that we have a rough idea that this is how binary form of the SQL statement is generated, let's quickly go through the order once more. So first thing that we saw was that tokenization happens. That was in parser, right? First was get token. So we generated the tokens. Then we saw that okay, there's a parser generator, and it says that okay, if this is the grammar rules, call this function. What was that function? So let's take the example of create table itself. So when we create table, it goes and calls this function, right? Start table. So this is what it pointed to, the parser. Now that it has pointed to this, I told you that one very important function inside this is read schema, and let's see why it is so important and why do we need to read schema. So when we say create table, so we are understanding the flow of create table right now, so focus on that. So when we say create table, first thing that we need to make sure is that the new table name should not collide with an existing index or table name. Because if I am creating a new table, there should not be an existing table or index with the same name. So you can see here I am reading the schema, and then whatever is there, I am going to say find the table with this name. Is it there? If it is there, then I am going to return the error from here itself. See, error message. That table already exists. Maybe there is a view, maybe there is a table, maybe it already exists, right? So let's see what exactly is happening inside this read schema. So if I go inside this read schema, there is a mutex that is being held, and there are a lot of things that are going to happen. I'm going to talk about the most important things. So there is one init function, and if we go further inside this, there is one init1 function. See, there are a lot of things that are going to happen. So there is one in-memory representation of schema tables that are created. We will talk about this in detail. But for now, what is most important thing for you to understand is exec. So if I go inside this particular function, see over here, this is what is called from initialize. And if you see, this is where you will be able to see the statements being called. See, first one is SQLite 3 prepare v2. This is where you are preparing the statement. Then this is where you are executing the statement. Here you should be able to see a step call. Where is it? Where is it? So yes, so this is the step call, right? So first call was the prepare call, then there is a step call, and after that we should be able to see a finalize call. So see, there's a finalize call. So this was the order which we saw also, but now you can see that how and exactly where it is happening. So inside the exec, so if you see, this is the function that is responsible for executing the SQL code. Whatever SQL code we had, we first tokenized it, we passed it, then we say, okay, start table. Now while initializing the table, we are saying, okay, execute the statements. First prepare the statement. That means prepare the binary form of whatever the SQL statement was given to us. Then what you are going to do? Then you are going to execute the statement and then you can destroy it. So when we say finalize, if we go inside this, you can see clean up and delete the VDBE after execution. Now, clean up and delete the VDBE after execution, where did VDBE come into picture? Okay, so we are finally leveling up because we are talking about VDBE, which is in the backend or the core of SQLite, correct? Before I move ahead, let me just quickly remind you that this video is not supposed to be easy. You're talking about internals of a database. It is one of the coolest things as a software engineer, right? You will feel very proud, and if you tell anyone, it is like so cool that you understood internals of a database. It is not supposed to be easy. So I am just talking about the main functions right now. But the more you go through this video again and again, and also when you see the debugging video, the next video, things will become just so much more easier. So stay patient. I do not want you to leave the video right now because it doesn't make sense leaving till here, because we talked about the first division. We talked about the front end of SQLite. We are finally getting to the core, the back end. So it doesn't make sense that you leave right now. So don't leave, okay? Stay till the end of the video. Let's understand what is happening in VDBE. Why did we get into VDBE suddenly? To understand, let's quickly go to the start of the file and see what's written. So it's written that this file contains code used for creating, destroying and populating a VDBE or an SQLite 3 statement as it is known to the outside world. What does that mean? That means that VDBE and SQLite 3 statement are actually the same thing. It is just that when we talk about the front end, when we talk in the first division of components, we refer to it as SQLite 3 statement. And when we come to the backend, the same thing is VDBE. See, VDBE or VM is a simple component. What it is supposed to do, it is just supposed to execute some instructions. Now those instructions are in binary form, are in bytecode. You're just supposed to execute it. So let me just show you this. Let me make things much more clear. So if we go back to where we called SQLite 3 VDBE finalize, which was our exec statement, right? So inside this, there was all the prepare, v2, step and the finalize calls. So if I go back again in this step function, now let me show you something very interesting. Can you see this? What does this mean? we are typecasting over here, right? So actually the VDBE and the statement that is there is exactly the same thing. It is just that in the front end and the back end, the different terms are used. And if you see this is there in all the functions over here. So let me actually show you. We are in VDBE API right now. So if I show you, you will be able to see this in a lot of functions. So can you see this over here? SQLite 3 reset. So same thing is happening over here, correct? Let's see. We'll be able to see it in more places, I'm pretty sure. Let me actually search these statements so that it will be easier. See, it is happening in step, it is happening in statement explain, in statement busy, in finalize. So you will see this happening in a lot of places, not just in this file, in other files as well. That statement is being converted to VDBE. This actually proves my understanding that statement and VDBE are essentially the same thing. I think it's finally time to see that how VDBE or VM executes whatever bytecode we have, whatever prepared statement we have, how does it execute? So how normal machines use assembly language? There is one language that is very specific to SQLite VDBE. You are not supposed to know it. It will not run anywhere outside. Even SQLite people say that it's specific to VDBE and you're not supposed to run it, not even the front end. It is specific to the core. So let's see what exactly happens. First, let's see the VDBE structure. So if we go inside this, this is how the structure looks like, right? So over here you can see linked list of VDBEs with the same VDBE.db. Now here you can see something called op, space to hold the virtual machines program. And if you go back, one very important structure that you're going to see is VDBE op. Let me just show that to you, VDBE op. So yes, let us go into this, and this is very, very important. So if you see over here, there is one opcode and then there are some operands. So this in very simple terms is the operation that VDBE is supposed to perform, and these are the operands. So suppose in very simple terms, suppose I have to do 2 plus 5. So 2 and 5 are the operands, and the addition, the plus, is the operation that we have to perform. So you can think of it like this, that whatever VDBE or the virtual machine is supposed to do, it is in the end some instructions that do this, do this, do this, do this, right? So every single instruction of the VM has an opcode and as many as 3 operands. So there can be max 3 operands. So most of the operations use, I think, 2 operands only. So there is one more that is used in some operations. The instruction is recorded as an instance of the following structure. So this is the operation that you have to perform, and these are the operands. Now you're thinking that, Keerti, where does all of this happen? So if we see the VDBE code, okay, if we see this, so do you see the switch statement? Let's see how big is the switch statement. And what is the switch on? The switch is on one opcode. So one, if you see, this is a massive switch statement where each case implements a separate instruction in the VM, right? This is in VDBE.c. And if I show you how big is the switch statement, 972 to 9055. That is how big one switch statement is. In actual simple terms, VDBE is nothing but a simple switch statement. Oh, this is the instruction to be run, I will run this, and this is how I am going to run it. So it doesn't do any optimization, nothing. It just has its own language in which it is going to implement a particular operation. So if you see over here, this is the switch statement, op go to. If we see this, so these are the operations that are possible, like go to or if not, right? So these are the operations that are possible. So based on these operations, so you can see there are so many operations, right? So based on each of these operations, there is one, like correspondingly, there's a case in the switch statement. So you can see this, right? So if I close this, there's another case for go sub, there's another case. So it is also showing that, see, this is the operation that you are supposed to do. This is how it is going to look like. Write the current address to the registered. So if it is go to, what you're supposed to do, you're supposed to do jump. This is the operand return. This is the, so there is proper documentation also that how this is done. So what is happening is that whatever bytecode was there in the prepared statement, now that is like divided into small instructions. So each opcode instruction, and then it is run slowly inside the switch statement that, okay, this is what we're supposed to do. So you will actually see this being run a lot. OP halt, that means stop it. So VDB halt, that internally calls OP halt. It means stop it. Then integer 6. So you can see these are all the switch case statements, right? And this switch is inside what? It is inside VDB exec, I think. So if I just search, yes. So this is the exec statement. And if we go inside this is where it starts, correct? So this is happening inside VDB exec. And if we see what is happening inside exec, so execute as much as of VDB program as we can. This is the core of SQLite 3 step. So SQLite 3 step is internally calling VDB exec. So now the flow is a bit clearer that, so when we have SQLite 3 prepare, so we are preparing the statement, then when we execute, what is it calling internally? The VDB exec. So that is where we are actually executing the statements, right? So if we want to see this, so if we go inside this and see where all this is being called, actually let's see where all is this being called. Let's see where is this called from. So this, if you can see, this is called from the SQLite 3 step. So inside step, what is being called? The exec statement, and this is how execution happens. And you will see this while debugging, that first we prepared, then while execution, what are we calling internally? The VDB exec. So now we have moved from front end to back end, and now VDB execution is going to happen. Since we are now discussing the backend part of SQLite, the core features, each of the components are going to be pretty huge, especially Pager. It itself has so many things to be done. BTree also can be a huge discussion in itself. So what we are going to do is, to make things simple, let's first make sure that we are able to visualize the entire flow of components. In the component diagram that we had discussed in the SQLite architecture in the beginning, what did we see? That VDB uses BTree, uses Pager, and then below that there is a OS layer. So at least if we are able to see this flow happening in the code, we will have some confidence, and then we can see each of these components in a lot more detail, correct? So for that, let me just open one very important function for you. So VDB logs, if we see VDB commit, this is a very, very important function. So if we see whenever changes have to be made to DB, we usually say that we are committing the changes, right, to the disk. So if we see in VDB commit, inside this, you will see there are a lot of BTree calls that were going to happen, like BTree enter, right? But the most important two calls that you should be thinking about is BTree commit phase 1 and BTree commit phase 2. We will discuss in a lot of detail that what is phase 1, what is phase 2. But to give you a quick context, do you remember in the starting we discussed that the entire DB file is on disk. Now we bring up a few pages on memory, and then we make changes in the memory, and then we push to the disk. Now what you should be thinking about right now is that what if DB crashes in between, because we are making the changes on memory, right? How do we make sure that the entire changes go to the disk, and in cases of crashing and all, how do we support recovery? So in order to all of this, we will understand phase 1, phase 2 properly, that how is this happening. This is a very common solution also in all the databases, not only in SQLite. We will talk about this in detail, but just notice that there are two things that are written over here, phase 1 and phase 2. So VDB internally is calling a BTree call, right? BTree commit phase 1, BTree commit phase 2. If I go inside this, if I go inside BTree commit phase 1, see internally it is calling Pager commit phase 1. So can you see the flow that from VDB we called a BTree function, from BTree function we are calling a Pager function. So the component flow is happening like that. Similarly, if I go to BTree commit phase 2, if I go inside this, see from BTree commit phase 2 we are calling Pager phase 2. So at least that flow should be completely clear now. From the starting, first we tokenize, then we parse, then we generate bytecode. Bytecode, we prepare the statement, which is nothing but a VDB pointer itself. Then VDB internally uses BTree, BTree uses Pager. Now beneath Pager, what will be the last layer? The OS layer. Now that you have understood this, let's see that finally how the data is stored on disk, how things are happening. Let's understand in a lot more detail. Since we just saw in the code that the commit happens in two phases, phase 1 and phase 2, it is time that we discuss that why SQLite does it in two phases and how does it actually happen. This will introduce us to a new concept which is not just applicable for SQLite, but a lot of databases use it. So this is pretty important. Listen very carefully. So what did we discuss in the starting? That SQLite supports ACID transactions, right? What does A stand for in ACID? It is atomicity. What does atomicity mean? In very simple terms, a transaction should either completely happen or it should not happen at all. It should not happen that a few steps of the transaction happen and the others did not happen. So a very common example that everyone gives, that I also give, is suppose there are two people, A and B, and 100 rupees need to be transferred from A to B. So there are two steps over here, that 100 rupees should be deducted from A and 100 rupees should be given to B. It should be incremented in B's account. So there are two steps over here. It should never happen that the money got deducted from A but it never reached B, and it should also never happen that the money got incremented for B but it never got deducted for A, because both of these scenarios can be disastrous. We need to make sure that the transaction either completely happens or it does not happen. Now let's discuss that what did we see in SQLite. What happens is that there is a disk file, and whenever we want to make some changes to it, we bring the pages to memory. So in this example, suppose we have to make the transaction from A to B. Suppose there are two pages where this data is there, and we bring the pages to memory and we update the values for A and B. So we did the transaction that -100 plus 100 in memory. Now what happened was that while we were putting these changes back to the disk file, maybe we decremented for A, we had not incremented for B. So just we did this and then entire crash happened, and maybe the disk file crashed or memory crashed or whatever crashed happened. So in case of crash, what do we do now? So now when the disk file comes back up, it will have no idea. So it would have the data that A was deducted, but B did not get the money. So what is going to happen now? This is not the expected behavior. We expect what? We expect atomicity from SQLite. So how should SQLite take this into picture? How does it handle this scenario? So to handle this scenario, there is one more component that finally comes into picture, which is called journal. So there are three things. One is the cache, one is the journal, and the other is the disk file. So let's see what exactly happens in phase 1 and phase 2. As you can see here, I have opened the documentation for commit phase 1, BTree commit phase 1, and let's see what it is saying. Okay, so this routine does the first phase of two-phase commit. So there are two phases, right? Phase 1 and phase 2. So let's quickly write that down. So commit phase 1 and phase 2. So what happens in phase 1? This routine causes a rollback journal to be created. So we are creating the journal. Okay, so create journal is what is happening over here. And if it does not already exist, and populate it with enough information so that if a power loss occurs, the DB can be restored to its original state by playing back the journal. So this has the original state. So when we load the pages to memory, what we do is whatever is the original state, that is pushed to journal. Okay, so that in case power loss occurs, so in case the crash happens, so if crash happens, so there is the original file that is there over here. So your disk file can always roll back to journal because the original part is already there, right? So what are we doing? If a power loss occurs, the DB can be restored to its original state by playing back the journal. That means that the original data, the original state is in journal, you can put it back to your disk file. This is also called rollback. This is called rollback. So what is rollback? That you're rolling back to the original state. There is also something called writing ahead. That means that you are making the changes. So in this case, I'm talking about rolling back. Then the contents of the journal are flushed to the disk. So when we say flush to the disk, we do not mean disk file over here. Don't get confused. So this journal initially also, obviously, whenever you make any changes, you are making it in memory. So what you're doing is you push the journal to disk. So we are pushing the journal to disk. And I will actually show this to you while debugging, that there is a journal file that is created, and you will be able to see that, okay, a new journal file got created right now because we are making the changes. After the journal is safely on Oxide, that means it is safely on the disk, the changes to the DB are returned into the DB file and flushed to Oxide. So you make the changes over here and then push to your DB. At the end of this call, the rollback journal still exists on the disk. So after this phase, that is after commit phase 1, journal file is still there on disk. Okay, it is still there on disk. The journal still exists on disk and we are still holding all the logs. So logs are there. The transaction has not committed. So after this, there happens commit phase 2 for the second phase of the commit process. Let's see what is happening in the phase 2. So commit the transaction currently in progress. So you can say this is the phase 2. Let's see what is written. This routine implements the second phase of the two-phase commit. So phase 1 does the first phase and should be invoked prior to calling this routine. So it is specifically mentioning that first phase and then second phase. First phase did what? Did all the work of writing information out to the disk and flushing all the contents so that they are written on the disk platter. So you made sure that the changes are done in memory and you made sure that they are put to the disk as well. All this routine has to do is to delete or truncate or zero the header in the rollback journal, which causes the transaction to commit and drop logs. So it is saying that this journal file that you created, dude, now you can delete it. Now it is not needed. See, if crash happened, we would have used this journal file. But now because there is no crash, we are talking about happy flow right now. We have nicely put the changes to the disk file. After we have done that, we can delete the journal. So that is what we are doing over here. All this routine has to do is to delete or truncate or zero the header in the rollback journal. So this is the rollback journal, right? In case crash would have happened, what would have happened when SQLite would have come up? It would have seen, oh, there are some changes in the journal, or the state of the journal and the state of the disk file is not the same. So either rollback can happen, so the original thing are there in journal, right? Maybe A was deducted and B was not there. So half changes are there in the disk file. So what SQLite will do is, it will see the original state in the journal and the disk file will roll back to the original state. So this is how we can handle crashes, correct? So normally if an error occurs while the pager layer is attempting to finalize the underlying journal layer, this function returns an error and the upper layer will attempt to roll back. However, if the second argument is non-zero, so this is like very code level, so I don't think we need to know this. This will release the write lock on the DB file. If there are no active users, it also releases the read lock. So this is very, very important to understand that there are three components. One is disk file, one is memory, which is the cache, and one is journal. For revision purposes and better understanding, I've also created notes which are available for free. I'll be adding them to Educosys. I'll be refining them a bit more and I'll be adding them to Educosys. You can check out, the link is in the description. So I've summarized it in very easy way. See, in SQLite, how does the update actually happen? So there are three things, right? One is cache, then there is journal, then there is the DB file, correct? So what exactly happens and how does it actually happen? Let's see. So cache is where the pages of the DB file are temporarily stored and modified in memory. So it is in RAM. By the way, don't get confused between this cache and the OS wala cache, because this is specific to SQLite. Okay. When a transaction is initiated, the necessary pages are loaded into the cache and any changes are made here first. In journal, what happens? Before any changes in the cache are returned to the DB file, a record of the original pages is written to the journal that we saw so that we can roll back. This ensures that if an error occurs, the changes can be undone, maintaining atomicity. This is what you need to understand. The DB file, once all the changes are safely recorded in the journal, the modified pages from the cache are returned to the DB file. This is the final step to make the transaction permanent. And this is where phase 1 ends. And in the phase 2, what do? You delete your journal, right? So the pager is the component that manages all three. It handles loading and modifying pages in the cache. It writes the original pages to the journal before any changes are made, ensuring that it can roll back if needed. It manages the final writing of modified pages from cache to DB file, ensuring data consistency and durability. So all of this is managed by whom? It is managed by pager, right? So this is how we are ensuring atomicity in SQLite. For reference, I have added simple notes for journal management as well. So a journal is a repository of info that is used to recover a DB when aborting a transaction or statement subtransaction, and also when recovering after an application, system or power failure. So it uses a single journal file per DB. So how there is a single disk file, there is also a single journal file per DB. It assures only rollback, undo and not redo of transactions. By the way, we will also cover that what all things are not supported in SQLite so that you have a basic understanding, because SQLite is designed to be simple and easy, correct? And the journal file is often called the rollback journal. The journal always resides in the same directory as the DB file does and has the same name with -journal appended. So I will actually show this journal file being created to you. SQLite permits at most one write transaction on a DB file at a time. It creates the journal file on the fly for every write transaction. So for every write transaction, it is created and deletes the file after the transaction is complete. So we saw phase 2, right? So that is when it is deleted. So this is called write ahead logging. I told you, right? This concept is not used just by SQLite but by many DBs, and we'll see this in future as well, to ensure durability of DB changes and recoverability of DBs in occurrences of application, system or power failures. Writing log records in the journal is lazy. SQLite does not force them to disk surface immediately. However, when before writing the next page to the DB file, it forces, so this is called flushing the journal. So flushing the journal means writing to the DB file. I told you, right, that first you make changes in the memory and then you flush them to the disk. So whenever you make changes from memory to disk, often the term that is used is flushing. Now that we have covered some really interesting theory about journaling, about caching, let's see some really interesting code as well. I'm sure you must be wondering that how does cache management happen in SQLite, right? So let's get to some really interesting code now. So here there is pager commit phase 1. Let's go inside this and let's see exactly what is happening over here. So firstly, we can see that pager flush on commit is happening and all of that. That's fine. Here can you see cache dirty list? What do we mean by cache dirty list? Let's go inside this. And if we see return a list of all dirty pages in the cache sorted by page number. What do you mean by dirty pages? So dirty pages in the cache meaning that we have made changes to these pages in the cache, but the state is different from the disk file. So when you have made some changes in the cache, but the changes are not made on the disk, these pages in the cache are called dirty pages. And let's see how they are managed, because there's a list of dirty pages, right? So let me show you something very, very interesting. Can you all see this? This is pcache, and if you see list of dirty pages in LRU order. So if you have ever heard of cache management, if you have ever read about it, either DSA, LLD, you must have come across a question of LRU caching, correct? And this is how SQLite also caches. It uses LRU order, and this is how it keeps the list of dirty pages. Let's see exactly what is happening. A complete page cache is an instance of this structure. Every entry in the cache holds a single page of the DB file. The BTree layer only operates on the cached copy of DB pages. Remember, I told you BTree component uses pager. So BTree doesn't talk to the disk file. Which component talks to the disk file? The OS. Above that there is pager. So BTree only operates on the cached copy. The page cache entry is clean if it exactly matches what is currently on disk. A page is dirty if it has been modified and needs to be persisted to disk. This is important. If it has been modified, if it needs to be persisted on disk, that is called a dirty page. And it has all the states, so dirty pages are linked to doubly linked list. So you can see PG header, so that is the header, there is next and there is previous. So this, you can actually see the entire implementation of linked list over here. So if we go through the function, see linked list management, the entire linked list code you can actually see manage dirty list. So you can see next and previous. If you do DSA, this is going to really excite you, because all of you keep saying, where do we see DSA in real code? See, this is database code. This is awesome, right? There is another function for number of cache pages. And then this is where you initialize the cache. So you can see you are making some configurations. Then there is shutdown. Then there is page size. Create a new page cache object. So there's like the another object, set page cache size. Then there is cache fetch. So there are a lot of functions over here. Obviously, this is like too much detailing. I cannot cover everything in this video, but this is just awesome, right? This is awesome. You have to agree. So if you also want to see PG header, so this is how it looks like. Every page in the cache is controlled by an instance of the following structure. So the linked list, so this is like a node in the linked list in simple terms. You can see this is the cache object page handle, and you can also see dirty next, dirty previous, number of users of this page, next element in the list of dirty pages, previous element in the list of dirty pages. So it's like the node of the doubly linked list, right? So you can go through this code. This is pretty awesome. As you must have understood by now, one of the most important components of SQLite architecture is pager. It does so many things that understanding pager itself can be divided into some modules. So I thought let's make a small diagram of that so that this will give you further clarity of exactly what all things are being managed by pager. So what did we discuss? That there is a component on top for B or B plus trees. Then there is the pager component. So let's visualize our pager component properly now. And below pager component is what? There is the OS layer, correct? So this is going to call the pager component, and the pager component, below the pager component, there is the OS layer. So now what all things does pager component do? So first of all, there is page cache because it does cache management, right? So this is like the most important thing. And in the OS layer, we do interaction with the DB file. So we can have like this, we can visualize it like this. Other than this, pager is responsible for taking care of our asset transactions. So we can say that it is also like a transaction manager. It is playing the role of a transaction manager for us, correct? Then it also plays the role of log manager because it is the pager that takes the logs over DB. So all the read-write logs that we take, whatever read-write logs that we take, you will be able to see that it happens in the pager component. Other than this, it also plays the role of a log manager. Now, what is a log manager? We discuss about journaling, right? So we have a journal file over here. We talked about write-ahead logging, right? That is what? That is called log management. So it is also playing the role of a log manager. So if you see that pager itself takes care of transactions, it takes care of logs, it takes care of cache management, it takes care of log management. So there are so many things that pager does. It's time that we get into the code of page and really understand it in a lot more detail. I have now opened the official documentation of SQLite because honestly it is just pretty awesome and it is very easy to understand as well. I have gone through a lot of it, and obviously the more you read, the more you will understand. Let's look at the most important point. So here you can see that they are talking about the DB file. So the complete state of SQLite DB is usually contained in a single file on disk, as we know, which is called the main DB file. During a transaction, so when a transaction is happening, SQLite stores additional info in a second file called rollback journal, as we know. So they have also explained about write-ahead logging in a lot of detail, how it happens, what is concurrency, how they handle concurrency, what is rollback, so how the crash handling happens. So you can read the documentation in a lot of detail. What I wanted to focus on right now is on the pages. See, the main DB file consists of one or more pages. We had visualized it in the starting, right, that there's a disk file and then it is divided into small pages. See, all pages within the same DB are the same size, right? So they are of the same size. The numbering starts with 1. So the maximum size, and they have mentioned all of this. But the main thing, okay, that you should understand right now, that at any point in time, every page in the main DB has a single use, which is one of the following. So every page in your disk file is one of these types. It is either a BTree page or a free list page or a overflow page or a pointer map page or a log byte page. So these are the only types of pages that are possible. Let's understand them in detail. So what is a BTree page? Now see, BTrees can be representing like a table or an index. So it can be either a table interior page or a table leaf page. Similarly, it can be an either index interior page or index leaf page, right? Why they are important? Because see, interior, so the root also is interior, by the way. So leaves are different and then interiors are different. Then free list page means currently unused. It can be used. Either all the pages are active, free list is not active. Then we have payload overflow page. What does this mean? Why is it needed? See, because page is of fixed size, sometimes what happens is if the payload is huge and it cannot come within one page, then for that we have payload overflow pages. This is an interesting thing, right? Because sometimes the payload can be huge. If it doesn't come within one page, then what? So that is why there are overflow pages. There is pointer map page, log byte page and all of that. So This about pages is very interesting because when we see the code, you can actually see, okay, this is a BTree page, this is a free list page and so on. So understanding this really helps a lot. Now coming to the DB file, the file itself, we will actually see the file and it has a format. So what happens is that the first 100 bytes of the DB file comprise the DB file header. Now this header is divided into fields. I will actually open the DB file and show you the first 100 bytes. You will be actually able to see that first it will say SQLite format 3. You will be able to see it that the top is over that. Then it will say the write version, the read version, everything. So the first 100 bytes, and it is given so nicely that see first 16 bytes will be this, then from 16th byte for size 2 this is what will be there, from 18th byte, from 19th byte. So for the 100 bytes it is given so properly, right? And they have given what is the page size, file format, version numbers. So they explained everything in a lot of detail. So obviously this is like too much detailing. We cannot discuss in that level, but I hope you get some idea. See what are BTree pages for this also, how does it look like? So again for that, what is the header format? It is mentioned, you will be able to see this again. Then what is a leaf cell, what is interior cell? Again, it is mentioned over here. What is a pointer map? What is cell payload? What are overflow pages, right? So going into that much detailing is obviously not possible, but the main things you should be able to understand. And I hope now you understand that how SQL table is represented. See this. Each ordinary SQL table in the DB schema is represented on disk by a table BTree. So each table has its own BTree, right? Each entry in the table BTree corresponds to a row of the SQL table. The row ID of the SQL table is the 64-bit signed integer for each entry in the table BTree. The content of each table row is stored in the DB file by first combining the values of the various columns. This is fine. Then there's primary key and all of this, right? Representation. Another important thing to say, storage of SQL database schema. So what happens whenever we create a table, there is one special table that is created, SQL schema, and we will see this table being created. When we create a table, this schema will be created. Why? You remember we read the schema and see whether there is a table that already exists with this name or with this schema or something like that. So that read schema, what are we doing? We are actually reading this schema. So when we create table internally, when I actually debug and show you, just create table internally, there are like around 8 to 9 SQL statements that get run. So you will see that the SQL run parser statement that we saw, that will be called like 8 to 9 times. That is why that is like a completely different video altogether, because within one create table statement, 8 to 9 times we will parse every statement. We will see exactly what is happening, because there will be a lot of things that we will be doing internally. We will be creating the SQLite schema, right? So we'll be talking about virtual tables and things like that. So there is alternate names. So there is SQLite master, there is SQLite temp schema, there is SQLite temp master. So you will actually see SQLite master and temp master. We will see this properly, right? So this gives you a rough idea of how things are stored internally. Considering how important pager is, we should definitely look at the code quickly. So you can see pager.c. This is the implementation of the page cache subsystem. Pager is used to access the DB disk file, right? It implements atomic commit and rollback through the use of a journal file that is separate from the DB file. The pager also implements file locking to prevent two processes from writing the same DB file simultaneously. Now this is very, very important to understand. Firstly, as we discussed, pager acts like what? Transaction manager. So it helps us with atomic commit or rollback. And because it is also doing journaling, it is also acting like a log manager. Now this statement is helping us understand that it is also acting like a lock manager. Why lock manager? See, firstly you need to understand that it implements lock on the entire DB file. Not on a table, not on a row of table, but on entire DB file. And when does it implement the lock? It prevents two processes from writing the same DB file or from reading the DB while another is writing. That means that while one process is writing the DB file, no other process can write or read. So write lock is exclusive. I am repeating this. This is very, very important to understand. What Pager does is it locks the entire DB file. So what we are doing is when one process is writing to the DB file, no other process can read or write. So the lock is exclusive. So our pager is acting like a lock manager, like a log manager, like a transaction manager. And here they have also explained the design of the pager, just how we saw how the header looks and all of that, right? So if you go down, you'll be able to see that. And also the state is also given very nicely. So the states of the pager can be open, reader, so writer, logged, writer, cache mod, writer, DB mod. And they have also explained that from which state can you transition to which state, like from open to reader, reader to open, reader to write, log, and how does it happen? So it starts in this state, and then what happens? See, I can create like a separate video altogether covering just about the pager, and let me know if this would be something that you would be interested in. I thought this is a very good overview, but if you want me to go into detailing of each of these components, I can actually do that. We have a lot of more databases coming up, and I would love feedback because this is like an entire series. Are you enjoying? If you would like me to go into more detailing for any particular component, let me know. I would love to do that. So here you can see the different states that are possible, how the lock is happening, right? So the locking states. So no lock shared, lock reserved, lock exclusive lock. So exactly when which lock happens. So that is also mentioned, right? That when error happens, when you can actually let it go, when exclusive lock happens, when shared lock happens. So it is just awesome. Again, I can go on about this. So one more thing I want to show before we end the video. So this file is obviously huge. This is about the pager because pager is like the most important part, right? Here you can actually see the code for moving the pages, how the journal management is happening, how the cache management is happening, cache move, mark it as dirty, drop it. So all of this exactly how it is happening, we'll be able to see this, right? Other than this pager, for BTree also, although we have like a separate video altogether covering BTree and why to these databases usually use BTree, but this documentation is also very nice that how it has n+1 pointers to sub pages. So the format detailing is mentioned. So how we just saw, right, that first we have a header string which shows SQLite format, and then there is page size, file format. By the way, can you see more light over here because it's morning? I have been recording entire night. So can you see some light more from this side because it is 6 a.m. right now. Cool. Anyway, I hope the entire effort of entire night, because I keep re-recording this and I keep trying to make the explanations as simple as possible. The entire effort of the entire night is going to be worth it if you can just hit that subscribe button and share. Just share with your friends or on LinkedIn or on Insta, wherever you are comfortable. It would mean just so much to me. Literally, it is morning. I can show it to you. I will put up an Insta status right now. It is morning. But cool, let's get back to it. So can you see file header, page header, cell pointer array? So this is how it looks like. OS level call. If you see the file over here is we have the entire command with us. We are back to the exec command, but now what is the statement that is going to be run? Select all from the SQLite master. Because we have given primary key, it is internally creating an index. What is the SQL statement? Insert into SQLite master. The values are, this is the index. As soon as we saw primary key, here was the second part of execution. See what is the statement? Update this set type table demo db journal. There is demo db journal. There is no journal. This finally brings us to the end of this video, and thank you so much for staying. It is just so awesome that all of you understand the internal architectures of a database now, of this SQLite. I mean, that is just so amazing. This is something that has been on my to-do list as a teacher since like forever. So it makes me really, really proud and happy, and thank you so much for being part of this and for staying till the end. Just remember that SQLite is designed to be simple and easy to use. So it does have some limitations as well, like it doesn't support alter table or it doesn't support all kinds of joins. It is designed to be simple for small to medium level applications, like for single user scenarios, or if there are multiple users, for low write scenarios. So keep these things in mind. Make sure you go through the code, you understand the SQLite architecture. I would love to see the discussions in the comments and let me know your feedback, because this series is going to be awesome. This is a free course and I hope you all are enjoying it. all the effort is going to be worth it if you could just hit that subscribe button. Please consider sharing it on LinkedIn or on Insta or with your friends. You have just no idea how much it is going to mean to me. I am putting all the effort into this, and I really hope this series is going to be successful. Thank you so much for all the love and support, and I promise there are a lot of cool videos coming up. In the next video, we'll be debugging the code, and it is going to be so interesting. You will see that within one create table statement, there are like 8 to 9 statements that are being called, and you will literally pull your hair. The first time I was debugging, I just couldn't understand why are we passing so many statements again and again. But trust me, it is going to be very, very interesting. So you just cannot miss it. So make sure you hit the notification bell icon as well. See you next time.